Single phase can be in the format of 220 volts or 230 volts, and three phase can be in the format of 400 volts or 380 volts. Note that if the voltage is not given, we use what we currently are using in a live active circuit, 400 volts for three phase and 230 volts for single phase. We will only use this single phase value and that three phase value if it is given. Alright, so then bear that in mind, that the percentages will just differ slightly. Alright, here we've got a single phase 230 volt AC supply. The DB supplies the following circuits in a conduit and is directly mounted against the wall. Circuit A, Circuit B, Circuit C, 4 kilowatt water heater 15 meters from the DB, 30 amp stove 4 meters from the DB, 1.5 kilowatt pool pump with a 6 kilowatt heating system 12 meters away from the DB. So it says you calculate suitable supply cables for each load and give a reason why the cable is suitable for the load in question. 6 marks. So you're gonna have to work out 3 sums: circuit A, circuit B, circuit C. Also says calculate the total voltage drop that is expected in the distribution board at full load. State whether it is acceptable or not and give a reason for your answer. Number 3, 2.3 would be what is the total load for this installation in kilowatts. I could only imagine it is the sum of all the power in kilowatt, and that would be the P total. Right, let's go. Circuit A, according to 2.1. Calculate the suitable supply cables for each load and give a reason why the cable is suitable for the load in question. Current for circuit A, kilowatt, 4 kilowatt, I equals 4000 divided by 230. I get an answer of 17.39. I select the cable 2.5 millimeter squared conductor. Because I found 17 amps, I would say it's so close to 20 amps that, start with a cable size of 2.5, because that would be able to handle 20 amps. I say voltage drop for circuit A equals MVAM times L times A divided by 1000. I find my value for millivolt per ampere meter according to my table. I would go according to my table here, and I used 2.5, and I see here 2 cable single phase would be 18, a value of 18, times my distance times my current that I've calculated divided by 1000 to convert the answer to volts. I find there 4.69. Therefore, use 2.5 millimeter squared conductors because the voltage drop is less than 5%, right? Less than 11.5. Right, next. Still question 2.1, circuit B. We've got here 30 amp stove 4 meters from the DB. I know 30 amps is protected by 4 millimeter squared cable, and I use that immediately. Then I use the same formula, and I then go to my 4 millimeter squared wire, and I see here that I can use 11 as a value, times it by the distance, and then also times it by the current given, divided by 1000. I get 1.32 volts, and I'm happy with this. I say 4 millimeter squared conductors is used because the voltage drop is less than 5%. That's a great voltage drop value. Then still on question 2.1, circuit C, I have a 1 kilowatt pool pump with a heating system, a 6 kilowatt heating system 12 meters away, and I say I want now the current for it. Again here, when I measure at the geyser, I measure the amps of the pump as well, and I add the two. It comes out to I equals a power of 7,500 over 230 volts, and I get an answer of 32.61 amps. Immediately I find that if it had been 30 amps, I could have used 4 millimeter squared cable, but because it's slightly higher, I go to the next cable size. And according to my experience and SANS, it is 1.5, 2.5 millimeter squared, 4 millimeter squared cable, 6 millimeter squared cable. So I would then not choose 4 millimeter squared, but rather 6 millimeter squared. And I then go to my table, I line up 6 mil with the correct column, and I have a value of 7.3 for the millivolt amp-meter. I times that by 12 meters, and also by the amps that I've calculated. I divide all of it by 1,000 and find an answer of 2.857 volts. This is a good value. I say therefore use 6 millimeter squared conductors because the voltage drop is less than 5%. Question 2.2 says calculate the voltage drop that is expected in the dB at full load. State whether it is acceptable or not and give a reason for your answer. I simply then take all the voltage drops of the circuits, because there's only 3 circuits, and I say VD total then equal VDA plus VDB plus VDC. So therefore all the voltage drop, the sum of that is VD total. I add it up and I find that my voltage drop at the dB is 8.869, literally 8.9 volts. This is acceptable because it is less than 5% of the total voltage. That's a great answer. Alright, there, and therefore this is relevant. Again, coming back every time to that maximum allowable voltage drop. Question 2.3, what is the total load for this installation in kilowatts? For 2 marks, a very simple formula that we derive. We say P total equals the sum of all the power values in kilowatt. Right, they want it in kilowatt. So the power for circuit A here given is 4 kilowatt. The power for circuit B, we use that same formula and we manipulate nothing. We just say 230 divided by the amps that they gives us 6.9 kilowatt. We inject that into the formula, and we then have circuit C where we add the 2 power values and get 7.5. The answer is 18.4 kilowatts in total. That would wrap up this question. That is the last question of this recording.